Okay, so we're going to look at today a little bit of an introduction to algebra. Unit 2 is basic algebra, problem solving, and then introduction to measurement and measurement conversions. So we're going to take a look at some of our basics of algebra first. And the most basic concept in algebra is this right here, an algebraic number. Now, some of what we've talked about, how numbers work, algebraic numbers are the same thing. They look very different because you get nervous about having that x in there or whatever letter we use for the variable. But just like any other number, it has two parts. The 4 here is a count, which tells us that we have 4 of something. And the x can be thought of as a label or a name. And just like any other number, that x behaves as a label, just like inches or feet or pounds or any other number we might have. And when we add our numbers, we had 4x plus 12x. When we add, first of all, we must have the same name, so we have x's and x's. We can only combine algebraic numbers that have exactly the same variable. And then we're going to combine the counts, the amounts. 4 and 12 make 16. Then we just keep that same name, just like we would in fractions. I can have things a little bit more complex than that, like 5x plus 7y minus 8x plus 2y. Now here, this is all addition and subtraction, so I can only combine things that have the same name. There are different names here, but that doesn't mean I'm completely done. I combine the 5x with, I have to be careful here, this isn't 8x, it's actually negative 8x. It's minus 8x. So 5x minus 8x, or you can think of it as 5x and a negative 8x, make a negative 3x. What's that? Perfect. So then we can combine the 7y and the 2y to make 9y. And we do have to have something to connect them. It's a positive 9y, so we put a plus there. So yes, negative 3x plus 9y. When we multiply, we don't have to have the same name. Here we have 3, which is just ones, times 5x as the name of x. We can go ahead and combine those. 3 times 5, combining the counts, is 15. And then combining the names. Now, at first glance, this might be easy to say, well, this is nothing times x. And when you multiply by nothing, you have nothing. But that's not quite the case. When there's no name written here, that's ones. And ones times x, anything times ones is itself. So that just stays x. It might make a little more sense if we look at 4x times 7x. So here there's an obvious name. We don't have that hidden name like we do in just the 3. There's an obvious name in each number. So we multiply the counts. 4 times 7 is 28. And we also multiply the names. X times x makes x squared. And when we multiply, we don't have to have the same name like we set up here. We could have 2y times 5z. Combining the counts, 2 times 5 is 10, and then also combining the names, y times z is just yz. When we're multiplying numbers, or multiplying these algebraic numbers, sometimes it is necessary to get just a little bit more complex. Here, these are just one-digit numbers multiplied by other one-digit numbers. Sometimes we'll run into a one-digit number times a two-digit number, like this. Now that looks very different, but this is really no different than having something like 3 times 42. When I do this multiplication, if I were going to do it out longhand, I would put the 42 times 3. Then I have to do the 3 times the 2 and then the 3 times the 4, right? Same thing basically happens here. That's 2x plus 7 times the 3 I have to do 3 times 7 is 21. It's positive, so I'm going to put a plus in front of it. And 3 times 2x is 6x. This is actually the full way, or the true way of multiplying those two numbers. Most of us have been taught a shortcut, though, called distributing. To distribute here, whenever you have a parentheses like this, where you cannot combine the stuff that's inside the parentheses. When we see a parentheses, our first thought should be, can we do anything inside of them? And here we cannot. So then we look at, is there anything that needs to be done to the parentheses? And in this case, it's multiplied by the 3. So that's where distributing applies, is when you multiply a parentheses, what you can do is just multiply each digit inside the parentheses by that number, which is exactly what we did here. We just did it out in a more formal way. The shortcut is to just take the 3 and go 3 times 2x is 6x. And 3 times positive 7 is positive 21, which is exactly what we got here. It's just this way is a little bit shorter and takes a little less paper. So the reason we need to be able to work with these variables is to do problem solving. And problem solving comes down to being able to solve things and work with things that look like this. X equals 7. It's an equation. And at the heart of it is this symbol right here, the equal sign. Now this is not as simple of a question as it seems. What does the equal sign mean? It's hard to define without using the word equals, isn't it? What the equal sign means, let's go ahead. Equivalent, that's actually very, very true, very good. The equivalent, were you going to say something? Same as, yes, same as. What it means is, what is on one side has exactly the same value as what's on the other side. So this and this are exactly the same value. In fact, you can think of an equation as being a balanced scale that balances around that equal sign. What's on one side of the equal sign exactly balances what's on the other side. Now, all equations that we'll ever work with start out in this form, as a variable equals a number, and they're built from there. What are some things we could do to build onto this? Well, we have our basic operations. Add, subtract, multiply, divide, powers, roots. Now, we're not going to do anything with powers and roots in these equations for this class, because we don't need them, really. But the other operations are fair game. So maybe we'll build onto this by adding. So let's add 4. So now this becomes x plus 4. But now if we add 4 to that side, it's going to tip the scale unless we do what? Add 4 to the other side. We have to do the exact same thing to both sides of the equation to keep it balanced. So 7 plus 4 is 11. Now this is the exact same equation we started with up here. We just put pieces onto it, built pieces onto it, make it more complex. Now, we're not so concerned in here about building equations. We will do some problem solving, but the way we build equations from that won't be necessarily like this. What we're going to be asked to do most often is to solve an equation. And when you're asked to solve an equation, what it's asking you to do is to take this equation back apart. Remove the pieces that have been built onto it. Well, this one was built by adding 4. So how do we take it apart? Subtract 4. Subtracting 4 takes that piece off, leaves us with x. Now again, because of this idea of the balanced scale, whatever I do to one side, I must do exactly the same thing to the other side. So I subtract 4 over here. 11 minus 4 is 7. So I'm back to that form of variable equals a number. X equals 7. Now this equation here, we built it. So we knew how it was built. We knew how to take it apart. The tricky part with dealing with equations is figuring out how it was built. Because when they come to us, they've usually been already built, and we're just taking them apart to solve them. So we might have y minus 6 equals 5. To figure out how the equation was built, we locate the equal sign, and then we identify which side of that equal sign the variable is on. That's over here. Now we ask ourselves, what is keeping our variable, in this case the y, from being by itself? Well, right now that would be the 6. What operation was used to build the 6 onto this? It was subtracted. So this equation here was built by subtracting 6 from y, from our variable. How do we take that apart? The opposite. We add 6. Leaves us with y. Now remember this whole balanced scale idea. If we add 6 to one side, we have to add 6 to the other side. 5 plus 6 is 11. Y equals 11. If we get to this point and we're not totally sure if we did it right, we can always go back to the original equation and double check. If y equals 11 is true, we should be able to put 11 in here for y, and it should give us the same value on both sides. So the left is just 5. There's nothing to change there. We replace y with 11 minus 6. 11 minus 6 is 5. So we get the same value on each side of the equation. We might have 9z equals 27. So we go through the same process. Find our equal sign. We identify where the variable is. It's right there. What's keeping z from being alone here? The 9. What operation was used to build the 9 on? It was multiplied. It's attached to the z through multiplication. How are we going to get rid of it? Divide it. We divide by 9 to make it go away, leaving us with z. Again, we make sure we do the exact same thing to the other side. We divide by 9. 27 divided by 9 is 3. We could double check this by putting a 3 back in here for z. 9 times 3 does equal 27. So we know that's true. Now, so far, these first few equations, you could have probably just looked at them and knew what number the variable had to be. So obviously, they're going to get a little bit more complicated. We'll run into something like this. So when we look at an equation like this, we find our equal sign, and we identify where the variable is. And here there's two things that's keeping the variable from being by itself. The 3 and the 2. The 3 was multiplied and the 2 was subtracted. So we have to ask ourselves, what was done to our variable? What was done to x to build this? Order of operation says you would do which one first, multiply or subtract? Multiply. So when this was being built, the first thing that was done to x is it was multiplied by 3. Then the 2 was subtracted from it. So now if you think about it, taking things apart, like we mentioned before, you're going to take off the last piece first. So you would add the 2. 3x, add the 2 here, you get 12. And then, of course, divide by the 3. X equals 4. These coming back to everybody? Okay. Well, we're going to make them more, for our purposes, we need them to be a little more complex. The stuff we're going to look at is going to look more like this. What would we do with something like that to solve it? Okay, yeah. The first thing we should always notice is the parentheses, which tells us we have to do something there first. Well, our parentheses has nothing inside of it that we can do. So we're going to go back to, what can we do to the parentheses, and that is being multiplied by the 3. And yeah, we could multiply it up the long way like I showed you a little while ago, or we could just distribute. To make it quicker, we're just going to distribute here. 3 times 2x, 6x. 3 times 7, positive 21, equals 51. And now it's back to that form where we know how to solve. What do we have to do first? Subtract the 21. So we're left with 6x over here equals 51 minus 21 is 30. And then Divide by 6. So x equals 5. What do you think? Doable? Let's do one more of those. Tell me what to do here first. Okay, so we're going to multiply by 5. 5 times 7x is 35x. 5 times negative 4, negative 20. And the 50 on the other side hasn't changed. So now that we've distributed, the parentheses are gone. What do we do next? Add the 20. 70 equals 35x. And then divide by 35. So x equals 2. Any questions? As we look at this one, we find our equal sign right here. When we go to locate our variable, what do we notice? You see the x appears twice. Now we're still thinking about that balanced scale here. You see x appears twice, but both the 3x and the 5x are on the same side of the scale. Can I take them and just push them together and make one big pile? Make 8x. Would that change how my scale balances? No, not at all. So then it's just like this. So we're ready to solve it like any other equation. Add 4. 8x equals 32. And then, perfect, divide by 8. X equals 4. And just like any other equation, if we weren't sure of ourselves, we could go back up and put 4 in here. Everywhere we see x, we replace it with 4. So this will be 3 times 4 minus 4 plus 5 times 4 equals 28. So the 28 ain't going to change. But let's do our order of operations here and see if we get 28. So 3 times 4 is 12. 5 times 4 is 20. 12 minus 4 is 8. Plus 20 is 28. So we get the same value on each side of the equation. So that double checks. We can also run into things like this. Here we find our equal sign. We look to see where the variable is, and we see not only does x appear twice here, but appears once on each side of the equation. We can no longer just push them together to make a big pile because they're not together, they're separate, they're on opposite sides of our scale. So what we have to do is just get rid of one of them. Normally we'll get rid of the smaller one. The 3x is the smaller one. To eliminate it, we have to add or subtract it. It's positive, so we're going to subtract it. Subtracting 3x makes it go away. Leaves us with 6 over here. We have to subtract 3x from the other side. The only place we can take 3x away from is the 5x. 5x minus 3x is 2x. Then we have plus 18. So now we can solve that equation just like any other. What do we do first? Subtract 18. 2x equals 6 minus 18 is a negative 12. And then Divide by 2. X equals -6. Any questions so far? Okay. So now our next step is to start trying to use these equations to solve word problems. You know, we might have some simple formulas like, you know, perimeter of a rectangle equals 2 times the length plus 2 times the width. And if you're told that a rectangle has a length of 18 inches and perimeter of 60 inches, find the width. So always take our formula. We know the perimeter is 60 equals 2 times the length. We're given the length is 18, so this is 2 times 18, plus 2 times the width. The width is what we're looking for, so that's going to stay 2W, 2 times W. Now, before we start solving the equation, there's things we can combine here. There's one thing at least. 2 times 18 is 36. And now this equation is in a form where we can solve it, just like the ones we were working with. Subtract 36. 24 equals 2W. Divide by 2 to get W by itself. 12 equals W. Now we have to ask and make sure that that is answering the question we were asked. We were asked find the width. W was the width. So the width equals 12 inches is the solution, the answer to the question we were asked. Now in that problem we were given every piece of information except for the one that we were trying to find. And then we just plug it into our formula and solve the equation to find that piece of information. Most of the time there's going to be a couple of pieces of information we need. For example, we might have the length of a rectangle is 3 times the width. The perimeter is 120 inches. So this time I have to find the length and the width. So we set up our formula here. P equals 2L plus 2W. The only piece of information we have is the perimeter, is 120. So we still have at this point both the variables L and W, the length and width. We can't solve an equation with two different variables. If they were both L or both W, we could do that. But we can't do it when we have one of each. So if I look at a rectangle, I have my length and my width. In this problem, is there anything that further describes either of those? Yeah, the length is 3 times the width. So L could be thought of as being equal to 3 times W, or 3W. So what that means is I can go to my formula here and I can replace L with 3W. This is 120 equals 2, instead of 2 times L, it's going to be 2 times 3W. Now we can combine 2 times 3W is 6W. And still more before we solve, we can combine 6W and 2W to make 8W. The 120 hasn't changed. Now we divide by 8. 120 divided by 8 is 15. W equals 15. Now, once again, we have to make sure we go back and answer our question. W is 15. That'll be inches, because we're given inches for the perimeter. That's one of the things we were asked, but we're also asked the length. Well, the length is 3 times W, so 3 times 15 will be 45 inches. Now we've answered the question. In fact, this one had 2 questions to answer. We're not so concerned about finding length and width. It's the type of algebra, the type of equations we have to construct from these that's the importance. There's one more type that we need to be able to deal with, and that'd be like this. Let's say we're told the length of a rectangle is 7 more than the width. The perimeter is, what do I do here? 94. Find the length and the width. So again, perimeter equals 2L plus 2W. We know that 94 is the perimeter. But we're still left with 2 variables. My length and my width. This time I am told the relationship between them is what? The length 7 more than. So that'd be the width plus 7. So over here I can replace L with W plus 7. So 94 equals, instead of 2 times L, it'll be 2 times, I have to use parentheses, W plus 7, and then plus 2W. So now I see parentheses. I'm going to have to do something there first. Nothing to do in the parentheses, so I'm going to multiply by the 2. 2 times W is 2W. 2 times 7, positive 14. And I still have this plus 2W over here. Nothing to do on the left side yet, but I can still combine 2W and 2W to make 4W plus 14. And then I can solve for W. I'm going to subtract 14 to get 80 over here. 94 minus 14 is 80. And 4W over here. And finally, divide by 4. 20 equals W. Now again, I need to go back and make sure I've answered my question. My width is 20, but I was asked for the width and the length. The length is W plus 7. So 20 plus 7 is 27 for the length. Any questions on these problems we've solved? So the forms of equations we've used for these problems are pretty much the forms of equations that we'll need for everything we need to do. So now let's talk a little bit about a solution. In medicine, we often have medications that are dissolved into a solution. So a solution has a concentration. That concentration is a percent. When we're looking at a solution, the solution has a total volume. Within that total volume, there are 2 parts. There's a solute and there's a solvent. The solvent can sometimes be referred to as a diluent. An example of this would be salt water. Salt is the solute, water is the solvent. If you mix it correctly in a solution, the salt disappears into the water, so you don't even notice it's there. But obviously you can taste it, and its properties are still there. It just visually disappears. So for our medications here, many of our medications will be a solution. Now there's something called a suspension that works a little bit different that we're not going to talk about in here, but we might mention a little bit later. But for right now, we're assuming that this solution will stay dissolved forever. It doesn't separate on you like a suspension does. So when you look at a solution, to figure out the amount of medication, the amount of the actual active ingredient, that is the solute, is equal to the total volume times that percent, that's the concentration. In fact, we often do it the other way. We put the percent first, but it doesn't matter. So if I have 80 milliliters of 15% solution, the amount of medication in that .15 is my decimal form for my 15%, times my volume of 80 milliliters. So you give me 12 milliliters of medication. So that solution contains 12 milliliters of medication. If we need to dissolve seven milligrams of medication into a 28% solution, how much, usually what we're dissolving our medication into is a sterile water. A lot of times we use the abbreviation NS. NS can stand for a couple different things. It can either stand for normal saline, which is generally a sterile water, or neutral solution, which means it has no medicinal value to it. It's just a carrier. So how much of this NS, this sterile water, do we need? So in other words, what we're asking for is what's the total volume going to be? Not total volume, well, that's total mass in this case, but total weight. So anyway, we need 7 milligrams of medication. We got 28% is 0.28 times our total volume or total weight. So now you would divide by 0.28, exactly. Divide by 0.28 makes that go away. This is T. 7 divided by 0.28 is 25. So we take 25 milligrams of total solution to carry that 7 milligrams of medication. Any questions? So what we're going to be looking at is mixing solutions, mixing different concentrations. So let's say we are going to mix 200 milliliters of 40% solution with 400 milliliters of 70% solution. And I want to know what my final concentration turns out to be. Well, what we come up with here is The amount of medication is what's being preserved. The amount of medication is the same before we mix and after we mix. So the total amount of medication is equal to the medication from solution A plus the amount of medication from solution B. Well, how much medication is in solution A? Well, it's 40% times 200 milliliters. So 0.4 times 200. Does that make sense? Concentration, the percent is a decimal, times the total volume. From solution B, 70% is 0.7 times 400. Has to equal, we don't know the concentration of the total solution. So that's what we're finding is X, that total concentration. Do we know what the total volume is? Well, we have to conserve volume. We added 200 milliliters to 400 milliliters. We better get 600 milliliters. Does that make sense? Total volume is conserved. So now it's just a matter of doing the math, combining what we can combine and solving for our variable. We have 0.4 times 2 is 80. I'm going to cheat here and combine two things in my order of operations. 0.7 times 400 is, what's it? 280. Very good. So 80 plus 280 is 360. That has to equal my X times 600. So I'm going to turn into 600X. Now what? Divide by 600. So 360 divided by 600 is 0.6. So 0.6 or 60% is the concentration of my final solution after I mix them. Now in reality, we're not just randomly mixing solutions together and seeing what we come up with. What we're going to be doing is we're going to be mixing solutions to get to a desired concentration. So let's say that we have 12% solution and 30% solution. We need an 18% solution. So the question is, how much 30% do we need to mix with 100 milliliters of the 12% to get the desired 18%. So we're mixing a 12% solution with a 30% solution. We're hoping to end up at 18%. Do we know the amount of the 12%? Careful. Yeah, we're mixing 100 milliliters of the 12%. We know the amount. Do we know the amount of the 30%? How much 30%? That's the amount we're looking for. So we're going to call that X. Do we know the amount of the final solution we're going to have? First glance, you'd want to say no, wouldn't you? But look up here. Remember, this amount plus this amount has to combine to make that amount, right? So down here, the same thing is true. Well, 100 plus X. Yeah. This amount plus this amount has to equal this amount. So 100 milliliters plus X is 100 milliliters, or 100 plus X. So now our equation, we change our percents into decimals. So 12%, 0.12 times 100 milliliters, plus 30% is 0.3 times X milliliters. That has to equal 18% will be 0.18 times 100 minus X milliliters. Why did I put minus? 100 plus X milliliters, sorry. Make my mouth work correctly. And now we have to simplify and then solve. So we have 0.12 times 100 is 12, plus 0.3 times X is just 0.3X, equals, here we have the parentheses, nothing to do inside them, so we're going to do the multiplication. 0.18 times 100 is 18. 0.18 times X is plus 0.18X. Now, just like our equations before, we have a variable on each side. When we have the variable appears twice, we have two choices. We either combine them or get rid of one of them. In this case, what are we going to have to do? They're on opposite sides, so we have to get rid of one of them. Usually we try to get rid of the smaller one. In this case, that'll be the 0.18. So we'll subtract 0.18x and it'll be gone. All we have left over there is the 18. We subtract 0.1x from the other side, we have to take it away from the other x. That's going to be 0.30, so we got the same decimal places. 0.30 minus 0.18 is 0.12x. Positive, and we still have the 12. Any questions so far? So now we have to solve for x. We'll subtract 12. 0.12x equals 6. And divide by 0.12. X equals 50. Okay. So that means this was 50 milliliters. What do you think? These will take a while to get used to, won't they? Let's do another one or two here before we're done. Let's say we have 72% solution and 88% solution. We need 84% solution. Our question is, how much 88% do we need to mix with 120 milliliters of 72% to get our desired 84%? So I'm going to slow down a bit on this one and point out my organization as I go. The organizing these to get them into the equation is the key. Once it's in the equation, I have faith that you guys can solve it. But it's getting it put into the equation that's the really tough part. So we have our ingredients here. Our ingredients are the things that we have. We have 72% and 88%. Then we need to have, what's our final product going to be? We're shooting for 84%. Now we need to put down, so that's the percents that we're going to combine, the concentrations we're going to combine. Now we need to write down what we know about the volumes. Well, we have the 120 milliliters. Which one does that go with? The 72. What's the one we're looking for? How much of the 88? So we're going to let that be X. Now the 84%, again, this volume plus this volume has to equal this volume. So what's going to go there? 120 plus X. And now it's a matter of just putting it into the formula. We have our concentration times our volume. 72% is 0.72 times the volume of 120 plus 88% is 0.88 times volume of X equals 84% is 0.84 times a volume of 120 plus X. So now we need to simplify. 0.72 times 120 is 86.4. 0.88 times X is 0.88X. 0.84 times 120. 100.8. 0.84 times X is a plus 0.84X. Now we have to get rid of one of the X's. The smaller one's the 0.84, so we're going to subtract it. So subtract 0.84X over here. Over here we have 100.8. Here 0.88 minus 0.84 is 0.04X. Positive, so I put a plus in front of it. 86.4. Now we solve for X. We'll subtract the 86.4. So 0.04X equals 14.4. And we divide by 0.04. X equals, what, 360? So that is 360 milliliters of the 88%. How are we doing? Now the next one, we're probably not going to get time to solve the equation, but I do want to show you how to set it up before we run out of time. For these, what we've done here is we've picked an amount for one of the ingredients and then figured out how much the other one needs to be mixed with it. But realistically, what we're going to be looking for is we have an amount of the finished product that we want. So let's say we have 21% and 30% solutions. We need 24%. So how much of the 21% and 30% do we need to mix to get 120 milliliters of the 24%? So again, we have our ingredients. We have 21%. We're mixing it with 30%. We're going to get a result of 24%, hopefully. The difference is now our amounts. The 120 milliliters is the 24%. It looks like we're missing two numbers here. We need the amount for the 21% and the amount for the 30%. This is where those rectangle examples fit in. I can't have two different variables, so I have to find some way to represent both of them the same. If I let the amount of the 30% be X, from what we saw up above, this plus this has to equal that, right? But we can work backwards. This minus this can give us that. So 120 minus X is the amount of that one. And I'm just going to set up this equation, and I'll make sure we have the homework. So this will be 0.21 times the amount of 120 minus X. Here this will be 0.3 times the amount of X. And over here, 0.24 times 120 milliliters. I'll trust that you guys can solve it from there if you had to. I'm going to give you the homework just in case we lose the network here. So on page 49 through 50, 1 through 43, the odds is solving generic equations. And on page 53 through 54, 1 through 15, excuse me, I'll just assign the odds, but if you want to go back and work on the evens, you can, because I know we're going to need more practice. We will start out with this again next week and work on these more, just so you know. So if you're struggling, there will be time. But please try some to see how you're doing, and we'll start out by answering questions and doing some more examples next week. So you guys have a great weekend.